Alright, we're going to go ahead and try this, see how it works. We're going to start off with problem 4 from the worksheet from yesterday, and we are looking at a question that's kind of in between questions 1 and 2. Question 1 just asks us to figure out the potential energy at the top of the hill. Simple enough, mass times gravity times the height. The second problem asked us then to find how fast it was going, so we took that initial potential energy, assumed it all converted into kinetic, and then that told us how much, or we could use the kinetic energy formula to find how fast it was going. So now we need to look at, or try to determine, at this halfway point, once the car has reached exactly halfway down the hill, or in other words, has traveled down a height of 21.5 meters, and still has another 21.5 meters to go, what are the energy components? Well, if he's fallen half of that height, then the potential energy essentially will have been reduced by half because he can only fall half as far again. So, based on what we found for our initial potential energy from question 1, we can figure out that at this point, his remaining potential energy should be half of that. Now, I know this problem asks us by starting out, how fast is it going at that halfway point? We're going to come back to that answer here in a few minutes. So we said that the initial potential energy, when he was just resting at the top of the hill, should have been about 420,000 joules. So at the halfway point, the potential energy should have changed and become half of that. So our new potential energy should be something along the lines of 210,000 joules. So the remainder then, the 210,000 that has disappeared, must have gone and changed into kinetic energy. Because we know our total energy has to remain the same, so our total energy still has to be 420,000 joules. If we know how much kinetic energy we have then, just like we did yesterday, we can calculate what our velocity should be at that point then. So we can say, okay, if this is our kinetic energy, and we know that our formula for kinetic energy, I'm just going to clear a little more space here real quick. I'm just going to try to clear a little extra space here really quickly. So if we know what our kinetic energy is, then we can plug that into our kinetic energy equation. So we know that we have 210,000 joules on this side. We have 1/2, our mass is still 1,000 kilograms. And then we have V squared still on this side. So if we work that out, we get V squared is equal to 210,000 joules divided by 500 kilograms. And then obviously to get the final answer we have to take the square root of both sides, and that'll give us the actual velocity at that point. So now we're just going to go ahead and pause for a second. Okay, now problems 5 and 6 both use the same half pipe arrangement. We have a snowboarder, mass of 80 kilograms, the height of the half pipe is 15 meters, and it's asking us to find how fast they're going down at the bottom of the half pipe. Now again, what we can do for that initial question 5 is calculate what the potential energy is at the top using our potential energy equation. So 80 kilograms times 9.8 meters per second squared times 15 meters. Squeeze that in there. And once we know that, we should recognize that by the time they get down to the bottom, all of that potential energy will have converted into kinetic energy. So whatever our kinetic energy, or whatever our potential energy is, our kinetic energy will equal that same amount. So essentially, we're using the number, or the value we get from solving for the potential energy, and that becomes our kinetic energy. Now, we then do the exact same thing we did before. We plug that into our kinetic energy equation, and we can solve for the velocity. So here is our potential energy plugged in for our kinetic energy. We know that equals 1/2 of 80 kilograms times v squared. Now here's kind of a key thing. You notice that there's an 80 kilogram on each side. And so essentially that's just going to cancel each other out immediately. We know that that's going to divide out to 1. And this is going to be true anytime we're doing these potential to kinetic energy conversions. The masses will always end up canceling each other out. We'll take a little bit closer look at that later, but understand that essentially mass does not matter. If this skater were 200 kilograms up at the top, they would be going just as fast at the bottom as the 80 kilogram snowboarder, assuming no outside factors, no friction, etc., etc. Alright, so if we rearrange this then to solve for v squared, that is just going to be 9.8 meters per second squared times 15 meters divided by that 1/2 factor. And then again, we have to take the square root of both sides in order to find our actual value for the velocity. Now, problem 6 essentially asks us to go in the opposite direction. Problem 6 says, okay, if we're going this fast at the bottom, then how high should we be able to go? So if we take this velocity factor and use it to recalculate our kinetic energy, and then work that back into our potential energy formula, we'll essentially should end up with a height of 15 meters again. We should find that we're going to go right back up the other side as far as we came down initially. And those are just that conservation of energy, assuming again that there's no friction. So I'll give you a few minutes to go ahead and work your way through the remainder of that problem before we take a look at the next one.